In this video, we're going to be covering the citric acid cycle and all the biochemical reactions that take place. So from where we left off, we saw that Acetyl-CoA was synthesized from the Pyruvate Dehydrogenase Complex during when pyruvate was converted into Acetyl-CoA, right? And Acetyl-CoA is a thioester. So before we get into the specifics of each individual step of the citric acid cycle, I just want to make a note of the generalized diagram here. So we can see here that I've color that, like before with glycolysis, and I haven't mentioned this explicitly, but I've always had a habit of color coding these things, so it's a little easier to keep track of what's happening in the reaction. So we see here that each highlighted step in green demonstrates that an electron carrier an NAD electron carrier is reduced, and we see here that for this particular step, this is the only particular step that's highlighted in orange, that this step shows the phosphorylation of ADP or GDP into GTP or ATP, right? And then we can see over here that FAD is reduced to FADH2, and that this is the only step that's highlighted. And we have to keep in mind, remember that there are two pyruvate molecules that were produced from glycolysis, right? So there would also naturally be two acetyl-CoA molecules that were synthesized from when pyruvate undergoes reactions with the dehydrogenase complex. So naturally, we'll expect to see a total of 6 NAD carriers reduced, 2 FAD carriers reduced, and 2 ATP or 2 GDP produce, or 2 ATP, 2 GTP produced. So let's just keep that in mind as we go through all these reactions. Alright, so let's start with the first step, where oxaloacetate is converted to citrate via citrate synthase. So we see here that that acetyl-CoA will react with oxaloacetate to form citrate via incorporation of the water, which allows for the transfer of the coenzyme A to form thiol-CoA. So I've shown out a list of descriptions for each reaction step here, but starting with the citric acid cycle step 1, or TCA1, we see here that the citrate synthase forms CC bonds. CC bonds meaning that a CC bond is formed between the acetyl group and oxaloacetate. To form citrate, right? And this is via a Claisen condensation reaction, right? And what is condenses is the acetyl-CoA, which is removed, right? And then in this case, we consider citrate synthase to also be a transferase, where the group being transferred is thiol-CoA or diol coenzyme A. Okay, so just one more look at this step right here. So a CC bond forms here. Okay, between carbon 1 of acetyl-CoA and carbon 3 of oxaloacetate. Now, TCA2 is broken into TCA2A and TCA2B, where citrate will form an intermediate called cis-acetonate before it's converted into isocitrate. So let's break down the steps of what occurs. So TCA2, for TCA2A, the enzyme acetonase appears to facilitate an internal redox reaction where C2 is oxidized because it loses H. So, and C3 is reduced, it loses the OH, right? So it gains those electrons. It gains electrons. So if what I'm describing here is that when it's appearing to facilitate when acetinase is appearing to facilitate an internal redox reaction, we see here that C2, or let me better write this down. C2 has full ownership of the electrons with H, right? So when C2 loses that bond with CH, it forms a double bond with the other carbon. So the electrons here are equally shared. So if I refer back to the diagram, we can see here that in cis acetonate between carbon 2 and 3, there's a double bond right here, right? Conversely, for carbon number 3, it's originally attached to an OH. It's originally attached to a hydroxyl group, where in this case the oxygen owns these atoms, but because a double bond is formed, we can see that the carbon that C3 now owns 2 more electrons than it did previously. So, it has equal sharing with the other with C2, but it gains 2 electrons, right? This line of reasoning may not necessarily be correct because even though I don't think C2 necessarily loses anything, because even if it loses its bond to hydrogen, or you know what, since there's equal sharing of electrons, no, I'd say that it still loses those electrons, but so it isn't necessarily a redox reaction. So that's why I said it appears to facilitate an internal redox reaction if we consider the rules that I described in redox reactions in the second video of this series. So in TCA2B, we see that the same enzyme facilitates the second redox reaction for rehydrating acetonate and reintroduces the water molecule, right? So we see here that C2 is oxidized, gaining the OH, and C3 gains the hydrogen atom. So it gains control of 2 more electrons. So that's in a sense, I can see that the overall process for TCA2A and TCA2B would be that the overall reaction is would be considered redox, since the oxidation states of some of the of these two carbons change. But the problem is that the overall redox, the overall oxidation state of the entire compound, so citrate, citrate and isocitrate, their relative oxidation states remain the same, right? All that changes is which atom is connected to which, right? So in this case, carbon 3 originally held the hydroxyl group, and now carbon 2 holds the hydroxyl group, right? So even if the individual atoms change in oxidation state, the overall molecule still has the same overall oxidation state. So we can't say that this is necessarily a redox reaction, and that we can't necessarily say that what acetoinase is an oxidoreductase. We would consider this reaction to be an internal rearrangement reaction, and thus the actual class of the enzyme is an isomerase. That's the key idea here. Okay. Now for TCA number 3, we see that isocitrate dehydrogenase is an oxidoreductase, and in this case, what's being reduced is NADH, or rather, isocitrate is being oxidized to reduce NAD to NADH, right? Now here's the mechanism that's shown below. So we see that isocitrate, we see here that there's a bit of an arrow pushing mechanism where there's a decarboxylation reaction that occurs here, right? This carboxyl group is pushed out, labeled as carbon number 4, since it's attached to the 2 oxygens, right? And we see here that what forms is a resonance stabilized intermediate over here, right? That this manganese ion is actually from some sort of residue from the dehydrogenase. So isocitrate dehydrogenase it contains a manganese ion that stabilizes these 2 charges, right? Because it has a positive charge of 2, so it stabilizes the negative charges formed here. That's why this reaction is favorable. We can also see that there's resonance stabilization where if you see in these yellow arrows that the molecule stabilizes because of resonance and the addition of prosthetic groups. Okay? So what we see here is that the molecule will accept the proton transfer from acid catalysis to form alpha ketoglutarate. Okay? Now, from alpha ketoglutarate, we see a second redox reaction, and we see here that a thioester is incorporated into the molecule, and we see a decarboxylation reaction as well, where we see that CO2 is removed from the parent molecule, which is alpha ketoglutarate. We also see that NAD is reduced to NADH. So if you notice this reaction here for the citric acid cycle for TCA4, it's very similar to Pyruvate Dehydrogenase Complex. So it's very similar to the synthesis of Acetyl-CoA as we saw earlier with pyruvate. So we can assume that all 5 of these cofactors are utilized, except for FAD. We can see that except for FAD, that the majority of these cofactors are used to support this reaction. Okay? And one more key idea here is that we need to know that there is the formation of a thioester, so a very high energy intermediate. Alright? Now this is a substrate level phosphorylation reaction pair. because a redox reaction occurs to allow for substrate-level phosphorylation to occur, right? So TCA4 and TCA5 are reaction pairs, or SLP reaction pairs. So for TCA5, we see that the enzyme used here is Succinyl-CoA synthase, or Succinic Thiokinase, right? So we see here that there's a phosphate transfer. The thioester created in step 4 can be used for incorporating in an inorganic phosphate while removing the CoA, right? So essentially, this is the overall reaction here that occurs. Succinyl-CoA, a thioester, will form Succinyl-Phosphate, will become another high energy intermediate. Now, this is what I believe to be the proposed mechanism. This is likely incorrect because it doesn't consider the prosthetic, not necessarily the prosthetic groups, but more of overall in a general context, the residues of succinic thiokinase, or the enzyme, right? So I believe here that the phosphate group nucleophilically attacks the carbon sp2 atom, which allows for an arrow pushing mechanism. And then we can see that there's the loss of the leaving group, which in this case would be the Succinyl-CoA group, which under acid catalysis could reform Succinyl-CoA, and what we're left with is the final product, which is the intermediate product, which is Succinyl-Phosphate, or the high energy intermediate. Now, Succinyl-Phosphate is a phosphorylated compound, right? So it is a high energy intermediate that can provide the free energy that can be used to do work, and in essence we can synthesize ATP from the cleavage of the high energy intermediate, right? Now, this is also a mechanism that's likely incorrect, but I believe it's relatively sound based on what's provided. So I believe that that Succinyl-Phosphate is nucleophilically attacked by some sort of nucleoside triphosphate, right? Which is in this case ADP, but it also applies for guanine as well, guanosine as well. So it can be guanosine or adenosine, right? And what happens here is that there's a nucleophilic attack, which, the arrows aren't here, right? Which allows the formation of a leaving group, and which allows the formation of a temporary intermediate. And what happens here is that we can see that there's an arrow pushing mechanism which allows for the loss of the leaving group, which in this case is succinate. And what's formed is ATP. This is likely not the correct mechanism, but this is the best mechanism that I could find for this reaction. Now, succinate will just undergo a simple yes. So this is the 6th step, which I told you before is when FAD is reduced to FADH2. So this is a different step where succinate is oxidized to reduce FAD, right? And it's reduced by succinate. The enzyme that facilitates this is Succinate Dehydrogenase, or Oxidoreductase. Now remember, this is the step of the reaction where the citric acid cycle and that connects. This is the step where the reaction that connects the citric acid cycle and oxidative phosphorylation, right? So we see in complex 2 in oxidative phosphorylation is just Succinate dehydrogenase, where succinate reduces QH2, and remember when I showed you the you guys remember when I showed the electron carriers, or remember when I showed the types of redox reactions that occur? These are the half reactions that characterize this overall reaction, where succinate is the one that's being oxidized, and the product here is fumarate, which participates in the next step of the citric acid cycle. And Q, or the quinone, is reduced to form QH2. Now these are separate reactions. Now complex 2B is a separate reaction that we'll go into much greater detail later on, but don't worry about this for now. So in the citric acid, in TCA 7, we see here that fumarate will undergo a reaction with will incorporate a water molecule to form malate, and the enzyme that facilitates this reaction is fumarase. Okay. Now fumarase in the reverse direction, so if we were to go from malate into fumarate in this direction, we would consider this reaction to be an enzyme. Why is that the case? Because water condenses from this reaction, right? Water leaves malate to form fumarate, but we're not going in the reverse direction. We're going from left to right. So we consider this reaction to be a lyase, primarily because there's a carbon-carbon bond break right here, right? Now, I also believe that the overall oxidation state of the reaction doesn't necessarily change. Yeah, no, the overall oxidation state doesn't necessarily change for this molecule, so we can't say that it is necessarily an oxidoreductase reaction. But we can, however, say that we can, however, be certain that in the next step that malate is definitely oxidized, right? Because we see here that in the last step of the citric acid cycle, we see that the malate is oxidized to reduce NAD. So this is the last redox reaction of the citric acid cycle. Okay. And this is different from the rest of the reactions because we see here that the overall oxidation state of the compound changes. This carbon here in particular is oxidized. There's no other carbon that on this molecule that is reduced. So we know that the overall oxidation state of malate changes once it undergoes a reaction with NAD to form NADH. Okay. Now, let's take a look at the grand total. So 1 NAD reduced per pyruvate. So if we take a look at the grand total if we consider all the electron carriers, all the ATP produced from glycolysis, pyruvate processing, and the citric acid cycle, we see here that there are, in the total, we see here that there are 10 NAD carriers reduced, 6 ATP or 2 GTP molecules produced, and 2 FAD molecules reduced.